Okay, so what we're now going to do is look at what the input files should look like, what should be going on there. So we're going to be looking at a couple of meshes. So for one, we're going to be looking at this Q8 plate hole one by one. What it implies there's a single element that we use here, one element here, and one element here. So there's 3 elements in total. I'm going to only look essentially what's going on in this input file here, and just show you more or less as to go. I'll leave it up to you to do the other 2 meshes on your own volition, but just to give you an idea of what do we expect to see in that input file for us to be able to model this. Okay, so what we need to see here is essentially on this edge here, applying consistent node loading. It's uniformly distributed load there of 2.5 MPa. That is one aspect. Okay, this height here is a height of 20. It was originally 40, and we only split in half, so that's 20. So if I take the essentially 20 millimeters and I multiply by 2.5 MPa, I expect to see a 50 Newton total load applied over this edge here. And then because I'm using this in 1.1 input file, that's a single element there. The total load over that single edge is then 50 Newtons. So I expect to see 1/6 times 50, 1/6 times 50, and 2/3 times 50 for the 3 nodes of that single mesh. Okay, that's one aspect. And the other aspect is on this left-hand edge, I would like to see, so this is essentially where x is equal to 0. I would like to see all horizontal displacements eliminated in the boundary condition. And here at a height of y equals to 0, I would like to see all the nodes that are on this y equals to 0 line, I would like to see all the vertical displacement being eliminated. So let's open up that input file and see what we see. If we open up that input file, we'll see essentially the nodal values there. We can talk about this element type in a second, because at the moment there's a 5 there, and so we should make it a 6. That should be plane stress. But bottom line is, if I look at x, let's get to the nodes that are associated at the bottom here. So let's just talk about these ones here. These ones here. So that's at x equals to 0. So that's essentially what I have here. So x equals to 0 is there, there, and there. So there's 3 nodes at x equals to 0. All the other ones are not. I would like to see there essentially all horizontal displacement being eliminated. And you can see all of the horizontal displacements are eliminated. Then if I were to look at this one here at the bottom, that's at y equals to 0, all of those nodes at y equals to 0. So this is essentially where I see this. That's 5, 8, 13, 15, and 18. 5, 8, 13, 15, and 18. I would like to see all the vertical displacements eliminated, as you see there. And then lastly, we would like to make sure we see the consistent node loads. As we said, 2.5 MPa times 20 millimeter height. That's a 50 newtons that we want to see as a total load being applied. So that's 1/6 times 50, 2/3 times 50, 1/6 times 50, and that's all in the x direction. And this is now at 16, 17, 18 as the nodes. Let's see where they are. 16, 17, 18, that is essentially at x equals to 40. And that is this right-hand edge. Okay, so Bob's your uncle. You can also double check that at least the mid-side one is node 17. So that's the mid-side node. That's the one that's in between the other 2 in terms of height. Okay, so that's all good and well. Just to show you again, all the element types should be plane stress. Okay, so just that we model it rapidly. Okay, now if you run through this and you say, let's take a look at this plate, Q8 plate hole. Let's run it. And if I show you more or less how it looks, we can see here, that's the original undeformed geometry. You can see this hole is very poorly represented. So if you use too few elements, you have a poor representation of the geometry, and if it's important to represent it accurately, you might have to refine it. So sometimes you'll refine because you need to represent the geometry better, or sometimes you refine because you want to have enough elements there to capture the response properly. So that's really the 2 main considerations. If you look at this, von Mises 8.3, if you look at sigma xx 8.8, what I'm going to compute every time at the bottom is k estimate, which is going to be the maximum sigma xx stress divided by the nominal of 5 MPa. And that nominal is again just essentially taking this 2.5 meganewtons multiplied by its area, which is then the 50 newtons that are applied. Then I divide by this cross-section area there, which is then the 20 millimeters squared. So it's half that, so it should then, that pops out as that is actually, in this case it's 10. So that 50 newtons then divided by the 10 millimeters squared gives us essentially the nominal stress of 5 MPa. Okay, so that's why I divide by 5 here for that 5 MPa. Okay, so the sigma xx, sigma yy, sigma xy. And that's all what we see there. So KT estimate 1.77. If I go for the Q8, and also just keep track of the time, but you can see the time is it's very quick. If I start going towards this one, all of a sudden let's look at what's going on here. So the time is it's 2 orders more essentially. So that's quite a lot longer that I have to wait. If I look at this now, there's essentially here 8 elements. So this square has got 8 by 8 elements there. Much better representation of the geometry. Look at that nicely formed shape there. If I look at von Mises 10.79, 10.83 sigma xx maximum. Look at that high stress there. Essentially, you can see here much lower stress down here. You can also look at sigma xy, sigma yy, and start seeing where the stress is high. So that's small compared to that large tensile load that we see there. And then the shear contribution is also quite small, again, compared to that large tensile contribution that you see there. Okay, so if we look at that, and we look at our KT estimate now, it's going to 2.1655. And then lastly, if I run this 64 by 64 one, I'll wait a bit longer. Can see much longer, but I'm waiting. Physically, we're just waiting now for this to finish. So this is important. This is now 64 by 64. So essentially 64 elements by 64 elements. So this is also 64 by 64 there. You can see there much finer resolution in elements if I zoom in. Okay, so you can see that. You can see much better representation. Well, a very nice representation there. If you just really compare it to this one, they're not that different if you just visually compare them. If you look at the stresses, it's gone up to 10.93 von Mises, 10.93 for sigma xx. Look at that beautiful stress view. Sigma yy, sigma xy. Okay, stress concentration has gone up to 2.186. So that's really what we have now for the stress concentration factor there. So if you look at the analytical film corresponds to the analytical film solutions correspond to the Ziegler estimate. And so if you look at the Ziegler estimate is slightly under predicting at 2.156, and the final elements solution that we have here is essentially 2.186. Okay, so that's really what we see here. But this is coming from the final element solution, and so what you're seeing is that the Ziegler estimates are definitely a little bit conservative in terms of the values that came out here. Okay. Also, the Ziegler estimate really one needs to ask yourself what kind of condition they looking at, because essentially in that Ziegler estimate, it's the width versus the whole diameter that really plays a role in what's going on here. And this is all of this is just essentially some kind of empirical approximation of what we see there. Okay, so what we see is we recover essentially an accurate representation of what the stress is doing at those places where we have stress raises because of stress concentrations. Okay. Okay, so that's without having to do any empirical stuff. This is just what comes out of the fundamental approach. Huge benefit that we get there if you start looking at that. But what you see is also, as I do this sort of, the first estimate is about 1.78, time very quick. Second estimate 2.166, not bad in terms of the estimation. Very quick solution 1.3, although it's essentially 2 orders more than that. Then again, going to the next mesh, really 2.186. This difference is really just 1%, about 100 seconds difference. So that's about a factor 70 or something that we're up there. So that's what we see here is essentially that huge difference in solution time, but not a big difference in terms of the accuracy of the answer. And what's also different, but not different, but I want you to pay attention to, because we don't have any singularities. We just have a stress concentration. This stress is converging beautifully. As we make the mesh finer and finer, we'll get more and more accurately the answer. and will converge more and more accurately to the correct answer. So that's important to understand. And we'll actually get a much better representation of this answer than you might find with some of the other estimates in terms of stress raises. Okay, so this is also something to take into consideration. If the mesh is too coarse, it's poorly approximate solution. Mesh to find way too long. Okay, so that's really what this boils down to. Just out of curiosity, what I'm going to do is I'm going to rerun these, but I'm going to on purpose make them now sort of a plane strain condition. And I'm just going to do this to you to show you more or less what the effect is of the way we model this 2D problem. Okay, so this is now going to be a plane strain scenario that we're going to be modeling here. Okay, going to make that sure. Okay, so let's just check. I just on purpose when I'm going to make a mistake here. I just want to make sure that this is the file in the right place and it's actually updating properly. So let me just run this. I'm going to rechange that value now. This is just to see that things are going ballistic. Yes, that's nice. So I can just make it back the way it should be. Okay. So that's something quick. Let's check. Okay, so if you run this case, so before I run it, let's just make it back to plane stress. I just want to run this and show you what it was and show you how it changes. So if you see there 1.77, that's what we had for plane stress. If I make it now plane strain, so 1.77, and essentially if I make it this, what I see here is essentially 1.781, so it's slightly higher with the plane strain. Okay, a little bit more constrained. If I look at Q8, I'm going to make this one also now plane strain, and then 16 by 16 is also. So all of them are now plane strain. So if I look at what the answer was here, 2.1655, 1655. If I run this now, I see 2.1657, slightly higher. And if I run this one again, what we saw here was 21859, 21859. And if I run this one now as a plane strain, let's run 21859. Let's see what happens. This is also just important that you understand. Just to show more or less, if you go for the two extremes, plane stress and plane strain, for this example, what the role of that is. That's something that we can nicely investigate. That's also not something that you really can investigate with Shigley factors. 2.1859, so essentially very similar kind of response that we see there for plane stress and plane strain, and we see that's sort of what we see there. Okay, but how we should model it is definitely not as plane strain, is definitely as plane stress. Okay, hopefully this gives you a good idea of what's going on in terms of for this kind of problem that we see here. Okay, so this is just to make sure that we can properly go and verify what's going on, get a good idea of what the solution should look like, and just to show you again, the finite element method really allows you to go and calculate, estimate the stresses, so that you can really get a good idea of what the effective stress concentrations are naturally. And as you make the mesh finer, you model it more and more appropriately around the place where you're interested in the solution, your estimate gets more and more accurate. So please take note that if you have stress concentrations and you need to resolve them, you really need to think about making sure that you have enough elements to be able to resolve that complex stress field around there. You can see here this kind of, just maybe I'll leave you with this kind of variation. The variation in the stress field is quite a lot. There's not a lot of variation here compared to what's going on here. You can see very quickly it's very high and it goes down. So we have large variations typically in stress fields, and the stresses, that's really where you want to say let's add more elements, where the variation, so it's not about the value, but the variation is quite mundane. You could actually get away with a much coarser mesh, still be fairly accurate. So that's really just to give you sort of some ballpark. So the take home of this is, when it comes to modeling finer elements, always start with the coarse mesh and then make it finer until you start seeing that things converge. If we had an intermediate mesh here, we might have had something that's already showing that this didn't change a lot. and that one might have just took 10 seconds to run. So if I had another intermediate mesh, 10 seconds plus 1.3 plus this is not even close to just one wrong choice of too fine a mesh. Always start coarse and make it finer. That's take home number one. That is really what's going on. And then check for what you're interested in, whether that has converged or it's starting to converge. Because I've got for 1% more accurate answer, I have to wait a hell of a lot longer. And that is not sensible. Another aspect is, again, as a take home is, you can imagine how much longer we would have waited had we modeled this thing as a full thing. This is a joke of an example. Had we modeled this as a full structure. So the exploitation of a symmetry already has given us a huge benefit computation of what's going on. Okay, hopefully this gives you a good idea of verification. So it's up to you to go and open up these input files. Estimate, before you do open them, you have to first, for me, do me a favor. You have to estimate what do you expect the consistent loading is going to be, yeah, and what the load on each of those elements is going to be for the 64 by 64 as well as the 8 by 8. And then you can go into the input files and check that it's indeed correct. Okay, so that's really what the rest of the lecture you should spend your time on. And then for those of you, yeah, so that's really just, I'll leave it at that. That's really what I think is a good, nice thing to go and double check for yourself. And then feel free to change. Yeah, it's going to be tricky to change it for the 64 by 64, but feel free to change some maybe the height of this plate so that this ratio changes, and redo the simulations. If you make this height maybe much more, you're welcome to try, and you can easily change those coordinates for the 1 by 1 and maybe for the 8 by 8 might be semi-tractable. Okay, but I think the bottom line is I would like you to spend time on factors like making just sure that you are happy with how these input files look for the other measures, and happy with how the consistent loading is also applied. Okay, thank you. Enjoy the rest of the lecture.